So here is conditional elimination. We'll look at the conditional introduction rule in just a minute, because that introduces a new feature to derivations that we want to deal with separately. This is one of your more useful rules. What it tells you is that if at any point in your derivation you have a conditional statement, and you also have something that exactly matches the antecedent of that conditional statement, those two things together will give you the consequent of the conditional statement. This is sometimes called arrow elimination. So for example, let's suppose we have the following two premises. And our goal is E and J. Well, what we could do here is to take the B out of line 2 with wedge or conjunction elimination. You'll notice that what we have here is a conditional, and in line 3 something that exactly matches the antecedent. That means that we can take the consequent and derive it, since these match exactly. And the citation will be 1 and 3 arrow or conditional elimination. Now, to get that ultimate goal, all we need to do is get the J by itself and join it with the E that we already have from conditional elimination. And we'll do that quickly, because that J can come right out of line 2 by and elimination. And then we can put lines 4 and 5 together with a conjunction introduction or wedge introduction, and we've reached our goal. Now let's look at a couple variations here. I'm going to take away the goal because we're just going to play around with possibilities here. Let's suppose I change line 2 so that it no longer contains the and B. Well, in this case, there's no way to get that E out, because we need something matching this exactly, and it just isn't there. So when you have a conditional, pretty much the only thing you're going to be able to do with it at this point is to look for something matching the antecedent, and then that will get you the consequent. But if you don't have that, you're never going to be able to get that consequent out of there. Another frequent error with the arrow is to treat it like a conjunction and just say, oh, look, I'll take that E from 1 arrow elimination. There's a couple of things wrong here that we can point out. First, there's no B. There's no antecedent to use with the rule form. Moreover, notice that the rule form always requires 2 lines, the conditional itself and the antecedent. Here, you've only cited 1 line. So either you've forgotten to cite something that's genuinely there, or as in this case, there's nothing else to cite. If you find yourself citing just a single line for an arrow elimination, then you should think something is wrong. So you can never get the consequent without also having the antecedent. And therefore you would have to cite some other line there. Another frequent error is seeing the conditional and then just trying to take the antecedent. Again, the fact that you're citing only 1 input line is a clue to danger. And in fact, you're never going to be able to get the antecedent right off of a simple conditional, even if, for whatever reason, you might have had the consequent by itself. Remember, you always need some conditional and then something exactly matching its antecedent, and then that will give you the consequent. For example, check out this derivation. Our goal is to derive c, which is buried in here in the consequent of the conditional in line 2. So that means we're going to want to try to get the antecedent of line 2, which is f, which is also buried in the consequent of a conditional. So we need the d. Luckily, we have the d right here, so we can start with the following moves. Notice, for instance, that line 3 is identical to the antecedent of line 1. That'll allow us to derive the consequent of line 1. So 1 and 3 together will give us E and F by arrow or conditional elimination. Now obviously we want to be able to derive B and C, because subsequently we'll be able to get the C out of there. In order to do that, we need to have F. And we have it here, but it's not yet on a line by itself. We could not apply arrow elimination to lines 2 and 4, because while there is a conditional in line 2, line 4 does not match the antecedent of line 2. Clearly all we need to do is to use conjunction elimination to get the F from line 4. Wedge or and elimination, conjunction elimination, all the same thing. Now line 5 does match the antecedent of line 2, so we can use those together to get B and C. And then, since we're ultimately after the C, another conjunction elimination, this time from line 6, gets us what we need. And there you have it. One final demonstration here. Two primary assumptions. Let's have our goal be to get C double arrow F. Now obviously C double arrow F is in the consequent of a conditional. So if only we have something exactly matching the antecedent, we can easily use conjunction elimination to derive what we want. Now looking at line 1, it is very much like the antecedent of line 2. So it seems like we might be able to go straight to C double arrow F and call it 1, 2 arrow elimination and be done. But in fact that's a mistake. The problem is, while we know that the antecedent of 2 and line 1 are equivalent, they don't exactly match. We have a very strict notion of matching here. It's a syntactic notion of matching. And in this case, A and B is very different from B and A. These are not the same, so we're not in a position to do a quick arrow elimination. We don't in fact have anything yet to match the antecedent of line 2. So let's get rid of our mistake. Obviously what we need to do is to somehow change line 1 from A and B to B and A. Now, since we know that those two are equivalent, you might expect that there's a rule that would just allow us to flip it, but there isn't yet. For now, what we need to do is take line 1 apart into its components. So we get A from 1 and elimination, B from 1 and elimination, and then put them back together in the other order with an and introduction. And now line 5 exactly matches the antecedent of line 2, which allows us in line 6 to derive the consequent. By an arrow elimination. And there we have it. Okay, the next rule we need to talk about is arrow introduction, or conditional introduction. Now this rule introduces something we haven't seen yet, and that is a subderivation. If you look at the rule schema, you see we've got our regular derivation line there. But this rule involves a subderivation with its own assumption and its own goal. What we're doing here is starting a subderivation with a single formula as an auxiliary assumption, and that formula can be simple or complex. And usually there'll be some work to do in the course of the subderivation until we get to another, usually distinct formula. So if we can show in this sort of case that our assumption P leads to some usually distinct result Q, then we're entitled to end that subderivation. You see the line stops there, and move out to the previous scope line and write a conditional which has the initial assumption of the subderivation as the antecedent and the endpoint of the subderivation as the consequent. We'll illustrate this with an English language example in just a second. But basically what we're showing with this subderivation is that if I assume P, and perhaps do some work in here, then I can reach Q, and that of course would entitle us to this conditional, if P then Q, right there. One other difference here is that when we cite our justification, we don't just cite two lines, we don't cite just the beginning and end of the derivation, but we cite the whole range. So it's lines I through J, arrow introduction. Now for an illustration. Consider this argument. Consider these two premises. If Ann goes to the fair, then Bob will go to the fair. If Bob goes to the fair, then Carol will go to the fair. Now neither of these premises tells us whether or not anyone is going to the fair, but as I'm sure you'll notice, they imply that if Ann goes, then Carol goes. Now here is how we could argue this. We don't in fact know that Ann goes, but let's suppose that Ann goes. This is an assumption. Call that line 3. Now, looking at 1 and 3, if Ann goes to the fair, then Bob will go, and we're supposing that Ann goes. This implies that Bob goes to the fair. So that's from lines 1 and 3. Now if we look at 2 and 4, if Bob goes, then Carol will go, and 4 tells us that Bob goes, then we get that Carol goes to the fair. Now, do we know that Carol goes based on just premises 1 and 2? No, we only got to Carol goes by assuming in line 3 that Ann goes. So what we can say is not that Carol goes to the fair, but we can say if Ann goes, then Carol goes. And this comes from the assumption we made in 3 and the process of using that assumption with lines 1 and 2 to make our way to line 5. So notice that I've indented these lines here. That's because they all start with this assumption and they all depend on that assumption. So essentially what we've done in our English language example here is a sort of subderivation. What this will look like in the symbolic parallel is the following. If Anne goes to the fair, then Bob will go. That's a primary assumption. If Bob goes to the fair, then Carol will go. That's another primary assumption. Now notice, the primary assumptions 1 and 2 neither tell us that Anne goes, nor that Bob goes, nor that Carol goes. We don't know that any of them goes, but we do know that there's an interrelationship between one and the others of them going. Now, in order to prove that if Anne goes, then Carol goes, A arrow C, we need to assume that Anne goes. We mark it with an A as an auxiliary assumption. And then we can proceed inside the scope of this subderivation to continue deriving things. So now we can work with lines 1 through 3. 3 matches the antecedent of line 1, so we can derive the consequent 1 and 3 arrow elimination. We continue both scope lines as the derivation continues. With 4 and 2, we can get C, again arrow elimination. Now we've shown in the subderivation that A leads to C, so we can, if we choose, end that subderivation and move out one scope line. And write a conditional consisting of the original auxiliary assumption in line 3 and the subgoal in our subderivation in line 5. And our citation for this will be 3 through 5 arrow introduction, or conditional introduction. So again, the basic idea here is we make an auxiliary assumption for a time. We show that it leads to some particular result, and then we're allowed to derive the related conditional. If A, then we can get C, so we get the conditional A arrow C. As you can see, the additional scope line and the horizontal to indicate the auxiliary assumption are like a miniature derivation inside of the larger derivation. In the English case, we indicate that similarly with indentation and marking the suppose and goes as an assumption. Now, a couple of points about the subderivation. It only ever starts with a single assumption, but that can be simple or complex. I kept it simple in this case. We'll see complex ones later on. That is, it could be D if and only if E, if that's what the derivation called for. Next point is we're always going to continue both scope lines, and we only end the subderivation when we apply the arrow introduction rule. There'll be a few other subderivation rules as well, and those subderivations end only when the particular rule is applied. Now, once ended, everything inside the subderivation is off limits. The technical term for this is everything inside the subderivation is inaccessible to lines below the subderivation. So let's see one more example of using the arrow introduction subderivation rule. Okay, Here's another derivation which is going to require us to use conditional introduction. Notice I'm keeping it relatively simple by just having two primary assumptions, although those formulas themselves are a little bit complex, and our goal statement is a little bit complex. One thing we'll talk about in a separate video is the goal analysis method. But you can see here that the main connective of our goal is a conditional, and one of the best ways to produce a conditional is conditional introduction. Now, since the conditional that results from conditional introduction has the assumption of a subderivation in the antecedent and the endpoint of a subderivation in the consequent, then we should think we want to try to do a subderivation which starts with this and ends with this. So we can set that up like this. We're going to start a subderivation in line 3. We'll draw a nice long scope line because we're not exactly sure how long it's going to take us. And we will take the antecedent of our goal here and put that in as our assumption. We mark it with an A for auxiliary assumption as opposed to a P for our primary assumptions. And now what we want to try and do here is reach not N and K. Note that if we can do that, then what we'll get is if D and F, then N and K, and we'll be able to end our subderivation and reach our goal. Like so. Now we haven't done that yet, so I'm just going to take the orange ink out here. But that is what we want to try to do. Okay, so now we have lines 1 through 3 to work with, and you notice that D is the antecedent of line 2. So if we take the D out of line 3 by conjunction or wedge elimination, then we can use 2 and 4 together to get the consequent. Those match, so those two together allow us to get the consequent of line 2. So we'll write K and not L there. That's 2 for arrow elimination. I see the antecedent of line 1 is not L and F. I've got a not L here on a conjunction, which means I can easily get that not L, and I've got an F here on a conjunction, which means I can easily get it. So we'll get each of those. We'll get the F from line 3, conjunction elimination. We can get the not L from line 5, conjunction elimination. And we're going to need a little more room here, so we'll move this down. That should be enough. And we'll extend our scope lines. So I'll put the F and the not L together in the same order in which they appear in the antecedent of line 1. That's a conjunction or wedge introduction. Those two together will get me the consequent of line 1, which is the not N. So that's 1, 8, arrow introduction. Still need a little more room. Scooch that down. Now I've got a not N in line 9. I need a K so that I can put it together and produce the goal of the subderivation. So I can get that K right out of line 5 here by wedge elimination, conjunction elimination, and elimination, whichever you like to call it. And now I can put 9 and 10 together with a conjunction introduction. And I'm almost done. Let's take a quick look back at what we've done, however. We started out with just these two primary assumptions, and this is our goal. But because our goal was a conditional and its antecedent was D and F, we did an auxiliary assumption of D and F. That allowed us to start some work with lines 1 and 2. And eventually we got our way down to not n and k, and notice that that is the consequent we were shooting for. So we've done our process of saying if d and f, then not n and k. So we can produce the corresponding conditional that this subderivation proves. So our line 12 starts with the antecedent d and f. That was our initial auxiliary assumption there. Arrow, not n and k. And so we'll cite 3 through 11, arrow introduction.